Good evening. I'm Kamala Gunawardhan again, coordinator of the Knowledge Sharing Subcommittee of Civil Engineering Sectional Committee. I welcome you all for today's presentation. We are now at the doorstep of the presentation from Engineer Lakshita Fernando. The title is BLASTS, Can Structures Resist? Actually, if I talk about little bit about him, he's a product from the University of Moratuwa. He has done his bachelor's and master's degrees from Moratuwa University. Also, he obtained his doctorate from the University of Sydney, Australia in 2020. Actually, at present, he is a lecturer of the University of Moratuwa in Department of Civil Engineering. The beauty of today's presentation is that he is going to present us the essence of his achievements through his doctoral thesis, which has focused on the development of a blast and impact-resistant multi-material system, and his experience in conducting field blast trials and high-velocity impact tests. We hope that he will present us many more interesting features about his theme here, blasts, can structures resist? Please enjoy. Over to you, Dr. Engineer Lakshita Fernando. Thank you.
Thanks for the introduction. Before I begin, the standard question at online meetings, am I heard well enough, and is the screen, can you see the screen?
Yeah, both all right.
All right, thank you. Thanks again for the introduction, and thank you to the Civil Engineering Sectional Committee of IESL, headed by Professor Tishanda Jayasinghe and his team. Thank you for this opportunity to present on this topic. Basically the intention of or the trajectory I hope to take in this presentation today, it's pretty much in the title, right? So blast, can structures resist? So if I were to give a quick overview of what I would share today, so firstly about blasts. So what is a blast, and how does it sort of begin, and how does it propagate as with time? And then secondly, how do structures respond to a blast event? We would see what are some of the techniques that we can quantify this blast, and how do we look at the behavior of structures if there were to be a blast. And thirdly, this idea of resisting. Under this third topic, first I'll be looking at some of the traditional method of resisting blast loads, specifically related to reinforced concrete structures and a little bit on steel structures. And the second part of resisting is where I'll be touching on some of the research work that I did for my doctoral studies, a more new, I would call it a more innovative method of dealing with blasts. So those are the three things that I hope to cover over the course of this presentation. This video, by the way, is a video you may have seen online. It's of the Beirut explosion last year. So before I move on to those three things that I explained, or rather introduced, just to give a quick idea, overview of the big picture, and why is this field of blast engineering relevant to us engineers? For one thing, explosions have started becoming a very common occurrence. Some of it is intentional and some of it is accidental. And us Sri Lankans we are no strangers to both these types. I've just put some of the headlines of some of the events we have experienced in Sri Lanka. Of course, the last one, the Beirut explosion, is abroad. We have as a nation, experienced in some cases intentional attacks. Those are carried out with the intention of causing harm to structures or to people. And in some cases, there are accidental explosions that are not planned, but that could still cause significant damage. For example, some of these gas explosions that we are hearing of nowadays, those are accidental, and also even the Beirut explosion, based on what has been reported, that was an accidental explosion as well. So it can take either form, but as this video, the video that's playing on the bottom right corner is suggesting, every year there's a lot of at least intentional attacks all around the world and causing serious fatalities to man. So continuing with this idea of big picture, it can cause serious damage to structures. And these structures are sometimes, when you think of BLAST, we would think these have to do with military structures. But once again, as I told you in the previous slide, in today's world, BLAST engineering is not limited to military. It's very much a part of, if I could use the word, the civilian life. For example, the trains that we travel, once again, we have experiences in the past in Sri Lanka, and even some of the critical buildings, once again, not anything new to us. An explosion in one of these could cause serious injury to people, as well as can cause catastrophic failure of structures. The military side of BLAST is, I guess, fairly straightforward. It's probably one of the main things that the military would want safety from, whether it's to do with armor vehicles or any other kind of military equipment. This idea of industrial structures getting damaged, once again, may not be very sort of common to us here, but in abroad, where there could be gas pipes that carry gas and oil for many kilometers, and an explosion in one of those could cause serious losses. And even in Sri Lanka, we have oil pipes. So as you can see, if there's an explosion in any one of these structures, and of course the list can go on, it could be quite fatal, and it can cause serious damages to structures. And of course, it's not limited to structures. We as engineers are also, I would say, our main goal is to save humankind, and then in doing so, we want our structures to be safe. And an explosion can cause serious fatalities to humans. And broadly speaking, when categorize the fatalities into two categories, as primary and as secondary. So primary is to do with the immediate explosion event. I'll explain what that is in the coming slides. Whereas the secondary injuries could be some of the after effects of the explosion. The primary injuries are the major concern, but even the secondary injuries can cause serious damage. So once again, this is not only limited to military applications, although the two photos I put on this slide are military related. If there were to be an explosion in somewhere, the extent of the explosion is not limited to the immediate vicinity. You can feel it further away. So that is why it is important to understand what's going on when the blast happens. To sort of sum up this idea of big picture, let me use an example. The example of say a roadside bomb that could hit an armor vehicle. So basically, one thing that could happen is the structure. The armor vehicle itself can get damaged. This is the structural side of failure. Or the person or the people inside the armor vehicle could be injured, or quite unfortunately could even be killed. So there are two things that we are interested in mostly when it comes to blast, and I'm summarizing it here in this slide. One is the excessive pressure. There's this idea that there's a sudden rise in pressure when there's a blast, and that pressure can be felt by the people inside. That can cause harm to the people, and that pressure can also cause harm to the structures. And secondly, what this phenomena called scabbing. Now that's to do with damage to the structure. When this happens, there could be particles that are ejected out of the structure, and those can act as high velocity projectiles. right? So those are fragments that were not part of the initial blast event, but can contribute to the negative impact the blast could have. So both these aspects affect, of course, what's called these traumatic brain injuries. This is commonly found in most soldiers, but even in people who are exposed to blast can experience these conditions. So I hope by this point you have an idea as to why blast engineering is important. It's not always very commonly followed when it comes to civil structures, but we live in a world that that quite sadly is no longer safe from whether it's intentional or unintentional explosion. So we as engineers need to be mindful of that to ensure the safety of our structures so that we can ensure the safety of its occupants. So from this point onwards, I'll be touching that first point I mentioned about blast. So I'll be talking about blast now and how does a blast occur and what can it do, right? Generally, the creation of a blast, we say that there could be shock waves. Sometimes we refer to as blast waves. The terms are sometimes interchangeable. There's generally a violent change in pressure. Now, this is not only seen in blast. Of course, things like the three images that I've given at the top also experience violent changes in pressure. But we are dealing with blast is a very unique situation, while all these things will have that violent change in pressure as the common factor. What we see in blast is a very, very unique phenomena. So this is what happens in a blast basically. So firstly, there would be an explosion, or there would be an ignition, or the explosion. Sometimes we use the word detonation. In the case of weaker explosives, we use the word deflagration. That just simply means that it starts. There is a blast. And the immediate thing that happens is there's an extreme rise in the temperature and the pressure. That's almost immediate. And it's very hard to even assign it a time. As you would see in the next slide, it is everything that I've shown here in this kind of the flow chart happens within a matter of milliseconds. So it's very hard to assign a time to this. So the sudden rise is then rise in the temperature, and the pressure is then accompanied by the expansion of the gas. So the air expands, and what happens is, as a result of this, a layer of compressed air, it propagates outward. So this is what we call as the blast wave. So there's a compressed air that is full of energy, that is at high pressure, that tries to sort of go away, that tries to move away from the source of the blast. So this is what we call the positive phase, but this doesn't stay forever. There is a sudden rise, and then that effect sort of decays. We say that it decays exponentially, it decays almost immediately. Because of the overexpansion of the air, there can be a reversal of the flow, and this is what we call as the negative phase. Now, this is an image I found on one of the recent publications. This kind of explains what I just explained, right? So the first image is where you see a tree, a dog, and a house, and there's an explosion. The red color mark, that's where the explosion is. So at the first point, everything's at peace, and suddenly there's an explosion. So when you come to the second picture, what happens is, so the explosion is at the right-hand side corner. So the effects are felt from the right to the left of your screen. So you can see that the tree has tilted towards the left, the dog has moved to the left, and the roof of the house, you can see the house is kind of skewed to the left, right? Next to this series of photos is a pressure time history, a standard pressure time history. So there's a rise in pressure. So the positive side of pressure is given to the left of the center line. The third photo is one where the tree has come back to its original place, of course, minus the leaves. The dog is lying dead, perhaps, and the house is not skewed anymore. So things seem to have come back to its normalcy, but the house has lost the roof and the tree has lost the leaves. So there is damage. And that's the third point on that pressure time history, where there is no, we say that's a zero pressure condition. So the pressure had increased and now the pressure is reducing. So at that point, things tend to come back to normal, but of course with damage. It doesn't stay there. There's that negative phase, which I explained earlier. So now the tree has moved to the other side, in the opposite direction, towards the blast source, and so as the house. And you can see, I don't know if it's clear, but the dog is also moving again. So it's getting blown towards the right again. That's what we call that the negative phase. And then that also doesn't last forever. The tree has come back to its original place. So it has lost most of its leaves. Now the house is further damaged, and the dog is lying still on the ground. So this just explains what actually happens during a blast. So let me put that into if I can put that into a graph and bring in more engineering terms. Now, I guess you have a fairly, at least standard idea of what a blast can do. But now as engineers, if I can put that entire sequence of events into words, right? So if there's a blast at some place, this is the pressure time history that you would see. So the pressure, as you could see, is in kilopascals, and it's quite high values, and the time is in milliseconds. As I told you, this entire event happens within a matter of milliseconds. So a couple of things that I want to sort of highlight here. Before the blast occurs, what you have is the atmospheric pressure. That's how you can call it, the ambient pressure. So for a few seconds prior to the explosion, everything's at that atmospheric pressure. And then there's a sudden rise. So you can see in the horizontal axis, I call it the time of arrival. So at a certain distance, within a matter of milliseconds, the blast wave arrives there. You can see even in the simulation that's running in the left corner, right? That red patch, that red contour, which is the high pressure, starts from the left-hand corner and it propagates towards the right. Right? So if you think of a point somewhere in the middle of that figure, it will suddenly experience this rise in the pressure, and that maximum pressure is what's called the peak incident pressure. And then it achieves that within a matter of negligible time. Basically, we are dealing with a millisecond time scale, but even in that, it's a sharp rise. You can't really assign a quantity of time to that rise. And then it decays. We call the decay is exponential. It reduces and it reaches zero, and then it enters the negative phase. It stays longer than, in terms of the time frame, it stays for longer in the negative phase, the pressure variation, but the magnitude is so much less, which is why generally when it comes to blast, we are mostly interested in the positive phase because that is what can cause significant damage. But there are things that are important to take into account about the negative phase as well. As I showed you in the previous slide, there can be reversal of flow, which needs to be taken into account. So the area under the pressure time curve is what's called the impulse. So these are the two the quantities that we are interested in as engineers when it comes to blast engineering, the pressure and the impulse. So you have a positive impulse and a negative impulse. Just a comment on the figure itself. Now the the air pressure generally is somewhere around 101 kilopascals, right? So this graph doesn't start at 0, it starts at 101 because of that. Even in a normal day-to-day life, we experience that air pressure. You can also plot this graph by starting at 0, then we would call it the overpressure. So that's the pressure that you feel over and above the atmospheric pressure. And so if you in a field blast trial, if you place a pressure gauge somewhere and you measure the pressure, generally what you would read is that overpressure. If I can use a different analogy, it's like when you go to pump air to your tires, right? If you empty the tire completely and take the reading, it's going to be 0 psi or whatever the units that's used. But that doesn't mean that there's no pressure. There is atmospheric pressure. So when you pump, say 35 psi or some quantity, what you mean is it's 35 psi over and above the atmospheric pressure. It's not that it's the total amount is 35. So similarly, in this figure, we are mostly interested in that overpressure. That is the quantity over and above the air pressure, because structures and us humans, we can handle the air pressure. We are somehow capable of handling that, but it's these excessive pressures that we need to deal with. Now this slide tells you, so this is a real case. There are serious increases in pressure and these are massive increases. So depends on the quantity of the charge size as well. But one sort of thing to do with blast that helps us though is that with the distance, there's a rapid reduction in that pressure rise. So if you look at the the plot that's see on the bottom left corner. So this is now it's a result from a simulation, but it's a validated simulation. So if there's a 1 kilogram explosion of TNT, and if we measure the pressures at 1 meter intervals from the blast source, this is what you would see. So the black line corresponds to 1 meter. So at 1 meter, you would have the pressure rising close to up to close to 1000 kilopascals. 2 meters is the light blue line, and the pressure only rises to about maybe 300. So you can see within a matter of a meter that maximum pressure rise has reduced, and then it keeps reducing. The green line is for 3 and the red line is for 4. So there's a reduction as you move away from the charge source, which is generally a good thing for us as engineers, because what this tells us is unless the blast happens in the immediate vicinity of a structure, maybe, not always, maybe we can sort of, our lives are made easy because there is this significant decay in the pressure. So there are a couple of parameters that we define to sort of explain a blast. One is the scale distance, Z. It's a function of the distance from the charge source to the location of interest divided by the mass of the explosion. Of course, we take the into power 1 divided by 3. So this parameter Z helps us to sort of quantify a blast event because it takes into account both the distance and the charge size. So I told you the charge size and the distance play a significant role in the pressure. So if we can quantify it using this single parameter, that's an easy way of quantifying things. So there have been many equations, empirical equations that have been developed by people in the past. And then in all these equations, you can see that the ZD is at the bottom, is at the denominator, which means as Z increases, so there are 2 ways of increasing Z. Either you can increase the distance from the charge source, or you can reduce the mass. So that's in either of those cases, your pressure will reduce. So these equations are able to somewhat capture the effects of the pressure. Of course, there are shortcomings in these equations, but what I want to highlight in this slide is when there's a blast, there's a sudden rise in pressure, but the effect of it reduces or decays as you move away from the source of the blast. Now, to add to the complication of that initial rise in pressure, now what we have is blast wave. So I told this to you earlier, when there's a blast, we can sort of think of it as a wave propagation event. So when there are waves, you will always have reflections, right? So if you look at this animation that's running on the right, the blue line goes and hits the barrier, and there's a green line, the green line that reflects. So what happens is there are reflected pressures when there are blasts. So if the previous peak incident pressure was bad enough, now this is worse because reflections can sometimes be 8 to 10 times more than the incident pressure. And in reality, unless the blast happens in no man's land, which is very rare, the effect of the reflections need to be taken into account, and that can increase the pressure in several magnitudes. That's a critical thing as well. So we need to take that into account when we think of a blast event. And also the location of the blast source also matters. We can have what's called free air blast, the left-hand side figure. So what that means is, so the black color box here is a structure, and the star is where the explosion happens. So you have a wave that propagates. So in a free air blast, the blast waves would hit the structure before it hits anything else. So generally the structure, so we can sort of visualize the blast wave as a spherical blast wave. When there's an air blast, so it's not necessarily free. What will happen is it will interact, part of it will go and hit the structure, but part of it will first hit the ground before it interacts with the structure. There are reflections, which means you are going to have a significant increase in the pressure that's felt by the structure. And you can also have surface blast, is when the source is on the ground. Then what we'll have is a hemispherical blast wave that will propagate outwards. And once again, the effects will have to consider the effect of the reflections from the ground. So depending on the location of the charge relative to the structure and also relative to the ground level, the effect that is felt by the structure is going to be different, because each case will present a unique situation of the way the blast wave propagates. So this is where the first bit of it, sort of the first area I wanted to cover, the blast side of things, ends. Right, so I just want to give you a brief idea of what a blast is. So my next area I want to touch is how do structures behave when there's a blast. I know there's a Q&A at the end, but if there's anything you want to clarify before I move on to the second part, I'm happy to do that now.
It's like no questions.
Right. Okay. We'll continue. Right. So by this point, you would have had you would have some kind of an idea of what happens when there's a blast. There's a sudden rise in pressure, but that pressure decays with distance. So these are some of the key things that we observe when there's a blast. So now when it comes to structures, so now we've sort of identified that there are pressures and impulses that we can quantify when there's a blast event. So now we want to know how do our structures behave when there's a blast event. So to understand this, first of all, we need to understand a little bit of the way materials behave when there's a blast, because structures are of course made out of certain materials, whether it's concrete or steel or any other kind of material. We need to sort of understand what really happens inside a material if you have to accurately quantify the response of a structure. So there are two ways of looking at this this effect of the blast. I've categorized it either as based on the strain rate on the left hand side, or I can also categorize this based on the response of the material. So let me explain what I mean by those two. So the strain rate, this is not something we generally use in our static loads, is to do with the strain divided by time. It has the units of 1/seconds or 1/time. You can also explain it in terms of velocity divided by length for a given element. So now why this is not generally used in static design is because we don't have to deal with velocity in static design. Our load is static, as the word itself implies. There's no effect of the strain rate. So that is why, as you could see here in this left-hand side figure, in this particular figure, so the strain rate starting from 10 to the power -6 increases to 10 to the power 0 and then keeps increasing to 10 to the power 4 and so on. So what we call our quasi-static loads, these are what we generally design our structures for, is in the 10 to the power minus region. So when it comes to earthquakes, the strain rate perhaps reaches somewhere around 10 to the power -1. And then we have our impact and blast loads, which are 10 to the power into the positive side. So this kind of, once again, shows us in terms of the load itself, the blast is in a different league of its own. So it generates high strain rates. And if you look at the based on the material response, in the lower ranges, we generally have the quasi-static response and the more general responses that we design our structures for. But as the strain rate increases, we need to take into account what's called the wave propagation effect, the stress wave propagation effect. Now, what this means is, if I can simply explain, to think of a beam and apply a static load, we would say that the entire beam deflects by the same amount. And we don't generally plot a variation with time. But if you think of this blast load, because it happens within a very, very short time, as I told you, within a matter of milliseconds, the application rate of the external load is significant compared to the response rate of the structure. It is not in a static load case, but it is in a dynamic load case, and specifically when you're dealing with things like blast. So the way to sort of quantify that is to think of waves propagating within a structure. Because what's felt at, say, the front of the structure is not immediately felt by the back of the structure. Now, that is not the case in a beam undergoing deflection under static load. We generally calculate the same deflection for the front and the back faces of a beam, or the top or the bottom faces of a beam. But in this case, what is felt at the front face is not the same as what's felt at the back face. So in order to visualize that, we can think of it as another wave propagation scenario. So in the air, we have blast waves propagating, and within materials, we call those stress waves propagating. So accurate way of understanding how to deal with blast loads in a structure means we need to take into account these stress waves. So the stress waves can also be further categorized into elastic stress waves, plastic stress waves, and shock waves. I'm not going to get into the technical details of that, but this is the kind of structural response that we are looking at. And also the material stress strain behavior is going to be very different. Now, the one on the left is what we're generally used to seeing. There's a yield stress, and post yield stress, there will be the plastic region, and there'll be maximum stress, after which the stress will reduce. But now, quite strangely, in the case that we are dealing with in BLAST, there is a increase up to the yield point, and we don't call this the yield point anymore. We call this the Hugoniot elastic limit. That's a property that takes into account the yield stress as well as the Poisson's ratio. And then beyond that point, there is a sudden rise in the stress. So this is almost like a fluid. So we call this the uniaxial strain behavior of materials. So what we are generally used to seeing is the uniaxial stress. But in this case, what we have is uniaxial strain. That means the structure doesn't have enough time to deform in the lateral direction. So the strain is uniaxial, only in the direction of the loading. So this then becomes a more applicable stress strain curve for this kind of an event. So this is what materials generally do when we are speaking of blast loads. But now when we get into the structure, the level of the structure, so now how do we sort of determine the response of the structure? This is the question that we're interested in as structural engineers. So I've titled this the quantifying the structural response. So one of the techniques that we have is using the single degree of freedom system. This is something we commonly use for dynamic loads. Or we can use, say, the energy theorems, because we know in a blast event there's energy that is dissipated as kinetic energy from the blast source, and these are absorbed as strain energy by the structure. So by comparing the two, we can also do an analysis. But this is a very basic way of quantifying the structural response. We make use of the basic single degree of freedom system equation. We can use things like the damp. I've excluded the damping here, but there's a certain level of damping in most of the structures. We can consider all that. We simplify or idealize the blast load as a triangle, not as the exponentially decaying one that I showed earlier. We can sort of approximate it to be a triangle, and we get, this is the traditional way of actually quantifying the structural response. And the question I want to leave with you all is this an simplification of the actual scenario? For one thing, we are simplifying the blast load, and is this able to capture some of the complex ideas that I told you earlier? Things like reflected pressure, it's very hard to quantify through this sort of a model. So this is where actually we need numerical simulations, finite element simulations, where we can actually model the blast event, simulate the blast event, and see the full picture. So I'll show you some of it towards the end of the presentation, but this is generally the way the structural engineers would quantify the structural response if it undergoes blast. This is good as a basic estimate. Another key thing now we want to know in terms of designing structures is also how much of structural protection should we offer a structure. Because the thing with blast, there are two things about blast that makes this idea of protecting structures very difficult for us. One is blasts are unpredictable. Now, it's not like, say, designing for static loads where we know the expected loads. You can design the structure to resist, say, 1 kilogram of TNT, but the next day someone can carry 10 kilograms of TNT. So there's no guarantee that the structures we design are safe for any given scenario of blast. The blast event itself is highly unpredictable. So there's only so much we can do as engineers. So we need to accept that we can only offer a certain degree of protection, and we need to accept a certain degree of loss. And on this, so this is a graph that sort of quantifies the costs involved with offering this protection as well as the loss. So this is not just financial, but also other economical and things like that are taken into account here. So as your protection level reduces from 0 right up to 100, your cost of protection will increase. So there's no cost of protection if you don't protect the structure, but if you're providing the maximum level of protection, you will incur a huge cost of protection. On the other hand, if your cost of protection is, your level of protection is 100%, then your cost of loss would be a minimum. But as you reduce your level of protection, the green line, the cost of losses will increase. So since these are two curves that are going in opposite directions, you can plot what's given as this red dotted line that will give us the point at which we can actually do an optimal and an economical solution. This is the best we can do as engineers. We need to accept that there needs to be a certain degree of compromise between protection and loss, because there is no way we can offer full protection, nor can we allow full loss, because we are responsible for the structures that we build. So it is important to be able to quantify what's the level of protection that we are going to offer to a given structure. And then we also need to be able to quantify the structural integrity. Now there's a couple of technical ideas that I'm presenting here in this slide. On the left-hand side is quantifying the response of the structure. So now your pressure range can vary from high to very low. As I told you, closer to the blast source, you have a high pressure. As you move away from the blast source, your pressure reduces. So in the region closer to the blast source, the pressure is high, and the governing factor for design is generally the impulse, because we call it an impulsive load. Now the idea in this figure that's given here is the time that the pressure is applied on the structure, the actual pressure is applied on the structure, is very less compared to the time it takes for the structure to resist it. So there's a difference in the time intervals between the way the load is applied and the way the structure resists it. And the resistance time is to do with the natural period of vibration of the structure, and maybe even the damping and things like that can come into play. So in this initial region, we are dealing with impulse, but as we go further away from the structure, we are mostly interested in the pressure, because the pressure acts for a larger time compared to the time it takes for the structure to resist it. So this is important, because when you're doing a blast design, we need to know, are we interested in the pressure or are we interested in the impulse? I told you the two main parameters that we can quantify to express a blast event is pressure and impulse. So we need to know which to use in what case. So if the blast source is close to a structure, we need to deal with the impulse. But if the blast source is further away from the structure, we need to deal with the pressure. And in the intermediate region, we need to make a judgment between which one we should use. In terms of quantifying the safety of the structure, we can develop these curves between pressure and impulse, and say for a given structure, if our pressure and impulse lies to the bottom of the curve, the structure is safe, but above the structure is unsafe. So this is a way of another way of quantifying the structural integrity. So we need to once again know whether we are dealing with pressure or impulse when we come to this figure. So that is that second part of the presentation that I wanted to cover. That is the structural response. So the first part I did was, how do we explain blast? How do we quantify some of the blast parameters? The second part is about how do structures behave under blast. So I showed you there are certain approximate methods that we have developed to quantify that. And then we need to also quantify things like how much of protection are we going to offer, and how much of integrity does our structure contain, a given structure contain. So we need to understand these two things before we move on to resisting. We need to know what the blast is, we need to know what our structure is. Then it gives us a platform to see whether it can resist it. That's in the case of an existing structure. In the case of a new structure, to design it in such a way that it can resist it. But all these different ideas that I've thrown out there are very important when it comes to the designing part. So in terms of the resisting, as I told you, I'll first deal with the traditional solutions. Now the idea of dealing with BLAST design is very important. As I told you, I've already explained the significance of it. So this slide, it's quite loaded with figures, but let me explain. So say you have to design a structure to resist maybe a certain level of threat, right? So over here are 12 steps that you can follow. Of course, some of these have got updated, but this is generally a good guideline to deal with. So first and foremost, where is the structure to be sited? See, what's the location of the structure? Now in this right hand side figure, there are adjacent properties. So now in some cases, we would not want that if these are critical structures, we want to move away from the vicinity of neighborhoods so that we can give sufficient level of privacy for those structures. But in some cases, you may not be able to avoid it. So then you have to factor that in. So we need to, first of all, identify the site. And what kind of a layout do we want? These are generally dictated by the use of the structure. And what is the function of the structure? Right now, related to that is the two figures that I've given here under types of structures. Generally, when we are dealing with BLASTs, you can broadly categorize structures into two types. One is barriers. So barriers are where you expect the explosion to happen inside the structure. So maybe because it is storing explosives, or now even the recent events in Sri Lanka, maybe there are gas explosions inside. So effectively, our structures are to be designed as barriers. So when you're dealing with the barriers, we are dealing with the internal explosions. So there could be internal reflected pressures. So we need to make sure that we design our structures to resist that. And to this end, we generally design, we have this idea of vented structures in a designing barriers. That's to make sure that it's sort of a more advanced version of the ventilation that we provide, is to make sure that the gases that can cause the explosives, as well as when there's an explosion, to make sure that the excessive pressure can move out of the structure quite easily. We are creating a free pathway for it to move out. So that is if our structure is a barrier. But most of our structures, more often than not, are shelters, because we expect the blast to be from outside. So we want to protect our structures from explosions from outside. So depending on whether your structure is a barrier or a shelter, your approach would be different. So that is why it's important to identify the function of the structure. Then you do the standard design for the static loads, and the fifth step is the important one, where you assess the threat. So you need, this is where we try to predict what kind of blast threats that we can have. So back in the day, as you can see in this figure, we thought that by putting a vehicle barrier, that way we are preventing from any heavy vehicles carrying explosives coming into the structure. So we thought that way we can avoid structures experiencing massive explosions. But we live in a day today where you don't need such quantities of explosives to cause serious damage. There are these things called improvised explosive devices, IEDs, where even small gadgets can cause significant damage. So assessing the threat needs to take into account the modern ways of explosions, and needs to consider some of the latest trends in terms of what we see around the world. So this is a very important step to assess the threat. Of course, we do this keeping in mind that we may not be able to predict to the exact point what the structure could experience. As I told you, you can design the structure for an X quantity of explosives, and the next day you might have 3X, which can cause significant damage. So we need to, assessing the threat is very much part of our engineering judgment. So then you can calculate the blast loads either using calculations, or you can run simulations. And then we also need to take into account the effects of fragments. I told you there can be fragments that can cause, that can be considered as high velocity projectiles that can cause serious damage. And as you go down in this, so we basically take into account some of the things that some of the other failure criteria that can occur due to blast. And then we do the preliminary sizing, and then we analyze the response of the structure. So this figure over here as you can see, they've secured the perimeter with a preventive wall. So we get blast walls along the perimeter. You would have noticed this in some of the embassies. We have quite tall walls, but more than the height, they are also quite strong in terms of they're heavily reinforced. And these are some of the things that we would see coming up in our city centers, bollards. This way we avoid, once again, vehicles access into our structures. But in some cases, you may not be able to prevent, you might have to protect. So these are two ways of protect. There are two ways of dealing with the securing our structures. Either it could be preventive, that way you're avoiding from any harm sort of reaching the structure. But in the case one of those, the structure is harmed, we want to protect it. So we protect some of it. So we'll be looking at some of it in the coming slides. So this is where now I'm going to enter into reinforced concrete structures. So we now understand that we need to decide what the function of the structure is. And the most commonly used material when it comes to building our structures is reinforced concrete. And generally for blast engineering, reinforced concrete structures is preferred. I'll show you why in one of the later slides. Now the material behavior under blast loads is also very important. Now I showed you earlier the accurate description of the material behavior. It's the uniaxial strain condition. That's where the stress suddenly increases with the strain. So what that would mean is the strength properties of a material also increases with the blast load. So we factor that in using what's called the dynamic influence factor, DIF. We use the DIF where we multiply the static property by that. So the DIF is generally more than one, more than unity. That way, actually, a dynamic property is more than a static property. So if you look at this curve, the dotted curve is for the high strain rate for the dynamic load, and the straight line or the line without the dots is basically for the standard strain rate. So this is for concrete. For concrete, you can see that as the strain rate increases, it's called the strain rate effect of material behavior, the strength properties increase, and it's the same for reinforcing steel as well. So the properties increase. So we take that into account by using this DIF factor. So in terms of reinforced concrete design, generally, now when there's a blast load, the reinforced concrete element will try to absorb it. So there's energy that is exerted onto the structure, and in the form of strain energy, the elements in the structure will absorb it. So under that, the elements will try to deform. So that is what you will get. You will get elements deforming. Now some level of deformation, the structural element would be able to handle, but beyond a certain point, you might start seeing failures. We call those spalling failures, where they can be either partial or total failure. So in order to determine what's an acceptable level of deformation, we broadly categorize the rotation at the support. You think of a simply supported beam, you get rotations at the support. So depending on the angle of rotation at the support, we classify the kind of failures into three types. So in the first type is where concrete is capable of handling the blast load on its own, as in the concrete as well as the reinforcement in it is able to handle the blast load. This is where if the blast load is small, it's able to handle it. But if the blast load is more, if the angle of rotation is more than 2 and between 6, the concrete will crush and it will not be effective in compression anymore. So we need both the tension and the compression reinforcement to carry that kind of deformation in the concrete. Although the concrete crushes, the concrete cover on both the surfaces will remain intact up to 6 degrees of rotation. So generally the shear reinforcements play a critical role in that. But beyond that, beyond 6 degrees, what you start seeing is that both the surfaces of the concrete element is going to get disengaged. So it's basically the tension and the compression reinforcement that will carry the load. And for this to work, merely having shear reinforcement won't be enough. We want what's called lacing reinforcement. I'll show that in the next slide. So depending on our blast load, the quantity of the blast, and maybe even the location of the blast, a concrete element can undergo 3 levels of deformation as it's quantified in this particular graph. So the shear reinforcement, generally we have the single hook shear reinforcement if the blast load is from one side, but if we're expecting blast loads from both the sides, then we need to have our hooks on both the sides to make sure we don't create any failure planes. But now this idea of lacing reinforcement is where it's like a spiral that connects our flexural reinforcement. So this is a more stronger connection between our flexural the tension and the compression reinforcement than the shear reinforcement. So you will get this for both the longitudinal and the transverse reinforcement. So lacing is a very important aspect if you're designing blast resistant structures using reinforced concrete. And also at the corners, there are what's called the edge effects. So there could be concentration of stressors. So because of that, you generally find diagonal reinforcement at the corners, as you can see in these red lines. So generally for blast resistant structures, we use either grade 30 concrete or higher. In terms of reinforcement, generally we use at least T12 or higher. So in terms of resisting itself, the shear or the lacing reinforcement plays a critical role. Now when you're thinking of steel structures, now I've given a list of sort of shortcomings of steel structures compared to concrete structures. Generally, if you're given the option of choosing between reinforced concrete and steel to design a structure to resist blast, more often than not, you would go for a reinforced concrete structure for several reasons. Generally, for close-in loads, the steel will not be able to handle it. And also there will be things like melting and things that comes into play. And generally in the reinforced concrete design, you can do the separate designs for bending, shear and for torsion, whereas in steel, all that is been combined into one design. So, and the sections can design the sections, generally we go for slender sections in steel. So you will get local instabilities and buckling that can cause serious effects. And also the joints, generally it's either welded or bolted. So those joints may not be as strong as some of our reinforced concrete joints that are heavily reinforced. So because of that, generally you will find steel not as the entire structural element, but as certain parts of a structure. For example, as a door. So when you're only sort of fabricating parts using steel, you are able to control the properties and come up with a structure that can resist. And also when you're thinking of steel, nowadays you get armor grades of steel that have very high yield stresses and ultimate stresses, but there's a bit of a compromise in terms of the strain. So it can't handle a lot of strain. Generally, a steel can go up to, on this scale, up to about 2.5, a normal steel, but some of these armor grade steels would fail before that. So although there's a significant increase in the stress that it can handle, there is a reduction in the strain. So the expectation is that because of the stress, they might be able to reduce the strain. But this is one of the shortcomings that you would see as steel as a structural material if you were to design entire structures using steel. So to sort of to wrap up the presentation from this point, this is the last bit where I'll present some of the more innovative methods of enhancing the structural resistance of structures and expected to undergo blast loads. So this is directly from the work of my thesis. Okay, I have a question. If it's okay, I'll soon answer that. Will the ductility or brittleness affect the behavior of structure during blast? Yeah, it plays a very significant role. I think I might explain that more in the coming slides with this idea of my thesis. You need ductility basically. Enhancing the reinforcement in reinforced concrete is a way of enhancing the ductility. And generally, the expectation is that you let the structure deform because there's a high level of kinetic energy that is exerted from the blast onto a structure. There'll be a lot of strain energy that the structure will have to undergo. So you have to let the structure to deform. When there's a significant energy, you need to let it deform. So if you want it to deform without failing, then you need the ductility, because if not, it's brittle. You will basically have catastrophic failures, right? So ductility plays a significant role. So coming back into this slide, so what I proposed in my thesis was a multi-layered system or a multi-material system. Now the inspiration for that is, of course, you see multi-materials and multi-layers in nature. Almost most of the things we see in nature are either multi-layered or you get multi-materials. And what we see here is the materials are arranged in a certain way that it can fulfill a certain function. So we in structural engineering or in the recent advancement in material engineering, we find this new class of materials called functionally graded materials. So what we do is we vary a certain function along the cross section of the material system. This will allow us to make sure that the properties of the structure is enhanced compared to only having a single material through the system. So what I proposed was an impedance graded system. So this property impedance is to do with the density times the wave propagation. So density is something we know. Wave propagation is that idea that I explained a few slides earlier. Now, when we are dealing with blast loads, we need to think of it as the structure getting loaded in the form of waves. So we have waves that will propagate through the structure. This is that figure again. So the accurate way of representing it, that is a structure under this kind of loading, is to consider the wave propagation. So because of that, impedance becomes a suitable candidate to design a material system, because by changing either the density or the material type, you can change these properties. So what I proposed was, if we arrange the materials, as you can see in this figure, in the reducing order of the impedance, with the material with the highest impedance facing the structure, facing the load, right? So we think of an incident wave, it goes and hits this interface between the first two materials. Part of it gets transmitted, part of it gets reflected. Right now, this is similar to what happens in an atmosphere. Not all the rays that are emitted by the sun reaches the earth. Some of it, I think, reaches the ground. Some of it gets transmitted, some of it gets reflected. Now that is to do with the properties of the different layers that we find in the atmosphere. Similarly, if you design the system in such a way that the impedance reduces through the thickness, we can cause some of the stress waves to reflect, right? So only part of it will get transmitted. This way we can reduce the effect of or reduce the magnitude of the stresses that a structure would experience. So that is the idea. Now this is a completely different approach to the traditional approaches. Traditional approaches are all about letting the structure deform and making it, sort of reinforcing it and making sure that it doesn't fail. But in this kind of an approach, we are basically getting to the heart of the matter, where we deal with the whole idea of wave propagation, and we are trying to sort of neutralize the effect of the wave propagation. So this way we are dealing with the problem at a more micro level. So in an impedance graded system, as you can see, I won't explain all these details on the slide, but what you would get is there is a reduction in stresses, as you could see in both the red and the green black lines. There's a reduction in stresses as you go through the material. Now the black line is for a material system with a high impedance reduction from material 1 to material 2 to material 3. There's a high impedance reduction. But in the red one, the impedance reduction is gradual. So what this tells us is, to maintain high impedance reductions within the system, you can significantly reduce the transmitted stresses onto a structure. But it comes at a cost. What this means is it has to reflect stresses at each joint, and it's these reflected stresses that can cause delamination between these multi-materials. So when you have more than one material in a system, you are susceptible to what's called delamination. To avoid that, we need to make sure that once again we strike the right balance between how much we want to transmit and how much we want to reflect. So this was the basic concept that I proposed in the PhD, and specifically in relation to BLASTS. So to test this idea, we have to fabricate a multi-metallic system consisting of steel, titanium, and aluminium. So the welding is the way that we generally connect materials. But normal, the standard way is the fusion welding. That won't do because these are different materials with different mechanical and thermal properties. So welding different materials is not an easy task. So we have to propose this rather innovative method once again called explosive welding. So what happens is, say if you want to connect the steel to the titanium plate, you place the titanium plate at the bottom, you place the steel at the top at an angle, a slight inclination, and then you cause an explosion at the top of the steel plate. And as you can see in the video that's getting played here, then what happens is without melting, because of the explosion, the steel will go and hit onto the titanium, right? And that in that impact zone, as you can see from one corner to the other, just like a jet that gets formed and moves away from the source of the explosion, causing the surfaces to peel and to bond well. So this was the new material system that we came up with using this technique. And then we tested that for two kinds of charges. One was for contact charges. This is where the charge source is almost in touch with the material. So we first tested a steel plate, that's the reference one, and then we tested a new plate, the multi-material system. So when we had a steel plate at the back surface, we saw scabbing. Now I explained what scabbing is earlier. This is where because of tensile failures, there are material that can get ejected out of the system at the back face. So we saw that there's scabbing in the, if there was only steel, that's the monolithic plate. But when we combined it with in the combined system with multi-materials, we didn't really see that. We saw a small rupture by sort of shearing, but that was because the aluminium that we used as the back material was slightly weak. So if we actually use a stronger grade of aluminium, we would have been able to prevent the damages, as you can see in the second figure. So if you compare this with what you see here, this new material system has been able to withstand the blast load. It has deformed. Obviously, it deforms. This is where the ductility comes into play. You can see that there's significant deformation. You cannot avoid that, but it does not fail. Now, when it's failed, generally when it deals with blast load, it's when the structures fail that we start to get worried. We also tested it when the blast source was slightly away, about 250 millimeters away from the plate, and this way of course the damage is much less. But what was interesting about this experimental setup was that we were able to get real-time deflection histories. We inserted an instrument inside what's called the blast rig here. This is a charge, this is the plate. So you explode this, then the plate will deform, and we measured the deflection using a deflection meter measuring instrument that was placed inside. So we were able to capture the variation of deflection with time. So once again, within a matter of milliseconds, all this happens. Right? Now the significance of this is what I put this here is when we use a simple quantification methods like the single degree of freedom system, you are not able to capture all this. You'll just get one final answer, maybe the maximum deflection or the residual deflection. But in reality, when there's a blast, there's more that's going on than the extreme values. So if you have to accurately capture those, you have to either do experiments or we need to use numerical simulations. So this slide shows you some of the simulations that we did. So this exact setup was simulated in this particular model. So what you see is you see the blast rig and it's surrounded by what's called the air domain. And if you can see the little sphere, the yellow color sphere inside. So we model it in such a way that we fill this sphere with the explosives and then we allow it to explode. And when that happens, you can see the material, the brown color material here expands out and it hits the structure, the red color structure. This is a pressure contour variation. So modeling it this way allows you to identify the pressure variations in the air as well as the deflection of the plate. You can get something similar to what the experiments gave you. You can get, if I plotted the deflection variation of the plate using this model, we have got something similar to what the experiments gave. So So what this system does, IGM is the impedance graded multimetallic system. What this allows you to do is, compared to only having a single material, we do what's called attenuating. That is, we are reducing the effect of the magnitude of the stresses that gets transmitted. So when you create barriers in a system, you can reduce the stress that gets transmitted. So by doing that, we are preventing any major kind of failure. So spalling is the critical failure in these cases. Spalling is effectively a tensile failure. So it's to do with the tensile stresses that get developed generally towards the back face, the face away from the blast. So what we are doing here is we are reducing the stress gradually through the system, so that by the time you get to the last material, our stresses have reduced significantly to the extent that you will not get tensile failure. Another way of enhancing the effectiveness of say steel to resist blast is actually using polymer or polyurea. So there was another experimental program that was done where polyurea coated steel plates were tested for the same blast setup. What we observed was, when you applied, we did a set of tests with polyurea at the front of the plate and then polyurea at the back of the plate. So having it at the back of the plate was more effective for the reasons I've given here. Of course, introducing a new material into the system would mean that your weight increases, but actually when you plot the gain in terms of the reduction in deflection with the gain in terms of the density, within a certain region, polyurea is able to reduce show beneficial action when it's used with steel plates. So that is another way of making sure that our steel structures are safe. So existing steel structures, you can add polyurea layers to it. That's like retrofitting technique, where we can make sure that we enhance the resistance of structures. So in conclusion, I've just listed down a couple of conclusions based on the three aspects that I covered. So the first aspect that I covered was what is a blast. So it's highly unpredictable and it's very intense. So which means it's a very challenging type of load to deal with, and its unpredictability is a serious concern for engineers. But within a certain theoretical framework, we have a fair bit of understanding how the blast load works. The second aspect I touched was how do our structures react, or what's the response of the structures when there's a blast. So if we are to consider that, my conclusion is that we need to consider a holistic design approach. The design for blast needs to be incorporated very early in the design stage. It can't be an afterthought. It has to, it's part of a broader design process that needs to be incorporated. And also in terms of resisting, this is the question that I answered as well. It's through enhanced ductility that our structures resist blast. We allow it to deform, but we don't let it fail. So we need ductility for that. So in line with that, some of the work that I presented, the things I did in my PhD work is related to that, where we increase the ductility through an impedance graded system. I would like to acknowledge a few people, Dr. Damit Mote, my PhD supervisor, who introduced me to this very interesting area of dynamic loads, and for most of the work that the latter half of the work that I presented here was work for my PhD. So grateful for all his supervision, and then the co-authors of some of the papers that we published are listed down here. I'm grateful for their support, and also for the support of the respective universities who helped us in some of this experimental work that we did, and also my research colleagues at University of Sydney who were part of some of this work. So once again, thank you for the opportunity to present this work in this forum, and thank you.
It's really appreciated, Akshita. I personally thank you, and it's a wonderful series, one lecture, and it's a sophisticated one, I hope. But anyway, I call Engineer Sapumal. Are you there?
Yes, madam.
Yeah, I think give a good thank you for this presentation.
Thank you, madam. Good evening to all of you. Actually, that was an interesting and informative session. On behalf of the Civil Engineering Section Committee, I would like to pay my gratitude to Engineer Dr. Lakshita Fernando for sharing your knowledge, findings, and experience on BLASTS and their effect on structures under the topic, today's topic, BLASTS can resist structures. So we were able to learn about latest findings on blasts and explosions and their impact to the structures and the blast resistant structures. And I think these findings and things we learned today would be very helpful for future design, as we learned many lessons on blast from our history. Dr. Fernando, I would like to thank you again for your valuable presentation on behalf of all the members and the participants. Further, I'd like to thank our chairman, Professor N.T.R. Jayasinghe, for your guidance given for arranging today's presentation, and all the committee members for your immense support. Also, I would like to thank management and staff of the ESL for the technical support and the publicity given for today's presentation. Finally, I'd like to thank all the fellow members and non-members for participating in today's event, and I would like to invite all of you to join with our upcoming knowledge sharing sessions. Thank you. Thank you for all of you, and good night.
On Pratap Ravindra is raised his hand. I don't know why. Is it?
Yeah, just a comment. Thank you so much for the presentation. I'm Ravindra from Sydney, and your presentation. I'm a pavement engineer, so we have our structures designed, as you said, for increasing strain rates and yeah. I have one little question. We apply wave equation to analyze FWD loadings on the pavement, like falling weight deflectometers. I don't know if this is out of the subject area. At what point where what we do and what you are doing differs? What is the cutoff point? Now, say we apply loadings on a pavement and we do exactly what you outlined, but your one is different. Your analysis technique is different.
Yeah, thanks for the comment. And yeah, so two types of dynamic loads. I think maybe that's the difference I may highlight. One is impact, the other one is blast. But both, the way of analyzing both is using wave propagation techniques. So I think that's where you find the common what you call the common point. That's where both impact and blast, you have to consider stress wave propagation within the material. The thing with blast though is because of the decaying effect of the blast load itself, when the pressure the structure experiences through the thickness of it also reduces, which makes it more prone for tensile failure at the back face. That's what causes the spalling. So in the case of an impact loading, generally we don't think of the magnitude of the stress reducing, but we still get spalling because of multiple interactions of stress wave within the system. So that I would say is the difference between the two cases. The common point is that stress waves need to be taken into account, but the difference comes in the way the magnitudes of the stress waves that a structure would experience.
Thank you so much. Thank you so much for the excellent presentation. Thank you.
Yeah, welcome.
Actually, sorry about the not allowing you to ask the question because there was nothing in the chat box. So we just proceeded the thank you message. Sorry about it, Pratap. And thank you for your questions. Okay. Shall we?
Yes, thank you very much, Dr. Fernando again, and thank you all the participants for attending today's presentation. Good night.